Sí, bueno, hola a todos. Muchas gracias por asistir a esta sesión del seminario. Hello, everyone. Welcome to this session of our seminar. I am honored to introduce our guest speaker, Professor Xiang Zhang from Shanghai Jiaotong University. He's a distinguished professor at that university. So thank you, Professor, for being here. And his talk is Analytic normalization of partially integrable differential systems near a periodic orbit with related properties. So, Professor, thank you very much.
Okay. Yes, thank you very much. I'm very happy to visit here. In fact, for me, this is the first time I visit Mexico. Since in August, I will attend the conference in the CIMIT Institute. Yes. So I first thank Professor Juan give me this opportunity to visit this university and give a talk to here. I have two talks. These two talks the topic are completely different. This is more theoretically. Another one is more application for concrete model. And also we thank all of you to attend these lectures. My talk is about the partially integrable differential system. This system has a periodic orbit. In case we studied several things. One is the main topic is about analytic normalization. So what is the partially integrable differential system? What is the analytic normalization? Now we talk about it. Yeah, so in this talk, we separate in three parts. First one is for the partially integrability. We give some background. The second one is for our new result. Then we give a very sketch proof on this our result. So in this talk, I report our result for these things. So we consider the analytic autonomous differential system in Rn. This system has a periodic orbit. This system is partially integrable near this periodic orbit. So we will study the partial integrability variety. We will explain what is the partial integrability variety. Then, if the system is partially analytic integrable, then we give a very simple expression, a symptotic expression of the functionally independent first integral. Then, use this result, then we study the analytic equivalence of the partially integrable differential system to the Bengali-Dirac normal form on the invariant manifold. Then we studied since we start the system is partially integrable. Then we start in these cases, what is the dimension of the submanifold? This submanifold fitted up with periodic orbits. The last one is we go back to the planar system. If the system has give a new criterion to characterize the system has an isochronal center, use the first integral. Yes, as we know, for studying the dynamics of ordinary differential system, if the system has some events, it's very helpful to study the dynamics. Of course, we know for mechanics or physical system, the system really has the invariance, but how to find the invariance is a difficult problem. And related to this subject, the most classical result is given by the Bengali and Diablov on non-degenerate monodromic singularity of a real planar analytic system. The system said, if a planar analytic system has an equilibrium, this equilibrium has a pure conjugated eigenvalues, then the system can be transformed to this form. Near the equilibrium, the system has the orbit is rotated about this singularity. So, yeah, for this system, the origin is the center of focus. So how to know the origin is of focus or center? So this is the equivalent characterization. The origin is the center if and only, this system has, the origin is the center if and only if the system has an analytic first integral in this form. This is the if and only if. And also, the equivalent characterization, the system is analytically equivalent to this system. So you see, this is the same. So we say, if system has a center, the system analytically, orbitally equivalent to a linear system. So that after time change, this is a linear system. This system right in this conjugate coordinate. This is a theorem given by Bengala and Diaplov. In fact, when we characterize this system one has the origin in the center of focus, usually we compute the Diaplov quantity such that the first sum of the Diaplov quantity equal to 0, then we get the condition of the parameter. After get the parameter, then we try to find the first integral. If we can find the first integral, then the system is the center. So this system only equivalent characterization, but this is really important to study this system. It has an origin in the center of focus. This is another equivalent characterization. So this theorem has many extensions to higher dimension system. Yes, Bengala also has another theorem. We can write this system one in a vector field. Then Bengala result says there exists an analytic function of formal series H. The vector field acts on this H. Then this act on this H. This is only composed of the resonant term. This is U square, V square. This is the resonant term. Only remains the resonant term. This is given by the Bengala. This is the K is the K or the Diaplov constant. So if we start the origin is the center of focus, if all this Diaplov quantity equal to 0, then the origin is the center. This is the center focus problem. Yes. Here we say the origin is the center. Then this system can be analytically transformed to this system. This system is a Bengala-Dirac normal form of this system. This is one kind of normal form. As we know, if we studied the dynamics of a nonlinear system near an equilibrium or near a periodic orbit, but this is really usually is a really difficult problem. But most of the time, we try to transform the system to a relatively simple form. Then we can compute. But for different subjects, the normal form is different. Here we consider the normal form in Bengala-Dirac normal form. Yes. Yes, related to the Bengala-Dirac normal form, there is a very classical result. In fact, in the last century, around from 1989 to 1992, Professor Itu published three papers under some additional conditions that prove that analytic integrable Hamiltonian system in the linear sense. This is if the system integral system can be analytically equivalent to the Birkhoff normal form in neighborhood of the equilibrium, but his result with some additional condition. So in the later on, in 2002 and 2005, this is a really beautiful work by the Room. Xiang Zhang is also with our university, with the 2 times. Just 2 months ago, he visited Duda.
Okay.
Yeah. he erased any restricted. He only proves that any autonomous analytic differential system equivalent to, in the Hamiltonian system, equivalent to the Berger-Hoff normal form. In the general system, to the Bengala-Dirac normal form. So these two papers is really beautiful result. Erased without any restriction. Only the integral system in the Hamiltonian system equivalent to the Berger-Hoff normal form. In the general case, analytically equivalent to the Bengala-Dirac normal form. About the general analytic system, we have some related result. Here is this paper published in 2008 with Invi from Georgia Tech. Now he moved to Canada. And also Jornadas. Jornadas maybe with here sometime.
He was here like 1 month ago.
Yeah. Professor Jornadas, Hala Pandasi, Sebastian Watch. I mean, this is from the Aachen. Okay. Sebastian Watch. And also myself with my student have some extension from this one. Yes. All these previous results for the analytic equivalent of the system, integral system to the Bengala-Dirac normal form near the origin. In 2014, my student with me extended this local analytic analytic integral system to a neighborhood of the periodic orbit. Okay. Just I mentioned the Bengala result. If the system, the planar system, has the origin, has a pure imaginary eigenvalues, then the vector field acts on some analytic or formal series, then the resulting is consists of the resonant term. So in 2014, is Valery Romanovsky is from the Slovenia, Maribor. This is Xia from China, and myself extend the Bengala result to higher dimensional system for the integral variety. I will explain what is the integral variety. So now we have started previously the cases started the integrable cases. Now we started the partially analytic integral differential system near a periodic orbit. We are interested in the variety, analytic expression of the functionally independent first integral, and also the regularity of the local normalization. Normalization means that we transform the system to the normal form, and also some property of the periodic orbit. Okay. Now we go back to the system. This is a system in Rn. We say that this system has a k analytic formal first integral h1 to hk. This first integral are functionally independent if the gradients are linearly independent in a full Lebesgue major subset. Is the usual definition. Now we consider the system 2. This system has a periodic orbit gamma with the period t, and also the periodic orbit has this expression x equal to phi t. So now we try to study the property near this periodic orbit. Now we use this translation. The system 2 can be written in this form. This is easy calculation. This is this is the linear part. This is the high order part in x. So this linear part is in fact is the variational equation of system 2 along the periodic gamma. This is a linear periodic equation. So then from the Fourier theory, this system can be transformed to the autonomous linear system. So this system, the linear part, can always be transformed to the constant system. This is a high order term, but this is periodic in t. But in fact, since we consider this system is an analytic system, after transformation, this system also analytic. But this is a periodic in T. In fact, in 2002, I have one paper with Wei Guni from Beijing University, German Libre from Universidad Autónoma de Barcelona, and me published one paper. We prove that this system can be transformed to autonomous system by a C infinity transformation. Analytic is not possible for C infinity. This periodic system can be transformed to the autonomous system. So this is an extension of the Fourier theory from the linear system to nonlinear system. This is published in 2002. Since we have a periodic orbit, so we have a periodic orbit. If we choose one point on this periodic orbit, then yes, we go back to here. For this variation equation always has one eigenvalues. This eigenvalue is exactly the Fourier multiplier along this periodic orbit. Okay. So now we start the system for this system. Since the system, analytic system near a periodic orbit always can be transformed to this system. So next time we will only start this periodic system. Yes, just we say this variation equation is a periodic linear system. We can define the monodromy operator and we have the Fourier multiplier. This Fourier multiplier always has one eigenvalue to 1, always has the eigenvalue to 1, and the other n minus 1 eigenvalues corresponding to the eigenvalue of the Bangala map. We have a periodic orbit here. So for the variation equation has n multiplier. One multiplier is 1. Another n minus 1 eigenvalues exactly since along this periodic orbit, we can define the Bangala map. This Bangala map is n minus 1 dimensional. So this map has n minus 1 eigenvalues. These n minus 1 eigenvalues corresponding to the Fourier multiplier. So now since we want to study the Bangala Dirac normal form, so now we want to give what is resonant. This is important. So this Bangala map is since here is a periodic orbit, is a transversal section, then we can define the Bangala map. This Bangala map is n minus 1 dimensional. So it has n minus 1 eigenvalues. This n minus 1 eigenvalue, we can define the resonant. If this eigenvalue is resonant if there exist non-negative integers m1 to n minus 1 such that the product equal to 1. So later on we will use the multiple product. This equal to 1 is called these eigenvalues are resonant. So now we define this set. This is d mu. D mu is a set of all these. Since this is resonant, maybe we have several members M such that this equality holds. So we define this set. And also define this set, we call it the resonant lattice. We define we use the dimension. This is not the correct notation, but for convenience, we use this one. Since this is not a linear species, so usually we cannot define the dimension, but only a notation. This notation means that this is the maximum number of Q plus linear independent element. This is the notation, means this one. we define this d mu. This d mu is, we will use this d mu to define the integrable or partially integrable. So please remember, this is the important notation. This is the resonant lattice for the corresponding to the eigenvalue of the rest of the Bungarlian map. In 2011, these are my students. We have one paper with German Libre. In 2011, proved that the n-dimensional system has at most d mu functional number of functional independent analytic or formal first integral. So this is this dimension. I said this dimension only a notation. This dimension controls the number of functionally independent analytic or formal first integrals. So if the d mu equal to n minus 1, this is the maximum number. N minus 1 is maximum. If the d mu equal to n minus 1 and the system has n minus 1 functionally independent analytic or formal first integral, then we say that the system is completely analytic integrable. This is for completely integrable. Now, if this d mu less than n minus 1 and the system has d mu functionally independent analytic first integral, then we say that the system is partially analytic integrable. This is the definition of in the title, say partially integrable. What it means partially integrable means that the system has exactly d mu number of functionally independent analytic first integral. The d mu is the maximum number of the Q plus linearly independent element in the resonant lattice. Of course, in the formal case, it's called the formal, partially formal integrable. So just do you remember? The original system, the autonomous system, had a periodical orbit. Then after the transformation, the system becomes system 6. 6 has a constant near part, and the high order term is the periodic in T. This is the periodic system. So to study the normal form, we expand this function. Let's go back to the system. Yeah, this system. This linear part is the constant part. This is the high order term. This in xt is the analytic function, but in T is the periodic. We expand this function. In X in Taylor series, in T is in Fourier form. We write this is the XL. XL is the multiple product. This is EIKT. I is a pure imaginary number. We expand the F. This is since F is n-dimensional. So this is Ej, J from 1 to n is for the Ej for the each component. For each component, we have this expansion. So now we say the eigenvalues, lambda eigenvalues of A, eigenvalues. In the F, for example, in the J's component, yes, this monomial, we call it pseudo-monomial. This is only a definition. This form is called the pseudo-monomial. In Ej is resonant if this K and L satisfy this equality. This lambda, this J corresponding to this J, a same J. This pseudo-monomial of system 6 is resonant if this condition satisfied. And this monomial, pseudo-monomial in first integral is resonant if satisfied. This do not have this one. So here is the one pseudo-monomial in system or in first integral are different. In system, the resonant is this condition. In first integral, the condition is this one. So now we define what is the Bengala dual normal form. Have this definition, now we say what is the Bengala dual normal form. Yeah, here is also for the definition of first integral. Yeah, this is important. Just we say for first integral, we have if the eigenvalue is resonant for first integral, if this quality satisfy, maybe we have several alpha k satisfy this equation here. So this is a set. Have this set, we define another one B without this k, this alpha. So now we have this G mu is the resonant lattice for the Bengala map, eigenvalues from Bengala map. This is for the R lambda is for here, is different. But all these three quantities are equal. This is important information. Later our proof use this information. In fact, this paper was published recently in Journal of Differential Equation. If you are interested, you can check the proof. I only mentioned this quote in quantity, and this one, the three are equal. So now we can state our result. Yes, this is at the beginning we have this. This is only notation. I wrote a sample. In fact, only this is a notation. The D defined is this one. So this is the extension of the classical Bengala result. So there exists a series of psi such that we take the derivative of psi along the system 6. We have here is composed only the resonant term. So this is the alpha k belong to R lambda. R means that this pseudo monomial are resonant. So this is the extension of the Bengala result from two-dimensional to higher dimensional near a periodic orbit. The second one, if system 2 is locally partially integrable, means that the system 6 has D number of functionally independent analytic first integral, then all these coefficients must be equal to 0. So this is for study. This is only a necessary condition for the integrability, partially integrability. Yes, just as I say, if the system is analytically integrable, it's partially integrable, means the system has D functionally independent first integral, then the system must have D functionally independent first integral of this special form. This is important. Since we know if system has a first integral, then any composition, any power, also a first integral. So this is very difficult to find the first integral. This theorem important is we can find only the first integral in this simple form. If system has D functionally independent first integral, then the system has D functionally independent first of this form. These are alpha 1, these are alpha 1 K1, alpha D KD, all resonant. This is the high order term, non-resonant. So we can find the first integral in this simple form. So this simple is simplifies the calculation to find the first integral. Yes. So just in the title of my talk, we have integral variety. So this set is called the partial integral variety if D less than n minus 1. If D equal to n minus 1, is called the integral variety. This is in the title we mentioned the integral variety. Yes. Yeah, okay. Yes, to prove this theorem, this theorem has three parts. First part means that the vector field there exists a series psi, the vector field acts on this psi, only composed of the resonant, pseudo-resonant term. Second one said this system is partially integrable, then all these coefficients are equal to 0. The third one say this partially integral system has this defunctionally independent first integral of this very special form. So this proof we need to use the Bengale-Dirac normal form. Yes, so here we give the definition. What is the Bengale-Dirac normal form? This is an autonomous system. We say if this system can be real or complex. If the system in Bengale-Dirac normal form, if it's A in Jordan normal form, we must enjoy. If not Jordan normal form, we cannot say what is the Dirac normal form. We must say A is in Jordan normal form, and this. See, now this system is an autonomous system. So the monomial only is this way. Xm is this G has m component. In the J's component, the monomial Xm is resonant. Resonant means that it's m times eigenvalue lambda minus lambda J equal to 0. If the system 6, a periodic differential system, is in Bengale-Dirac normal form, means that it also A is in Jordan normal form, but this here is a Gx has a T. This is here is F. In my 6 is F. F consists of resonant pseudo monomial. Means that here is the here is the pseudo monomial is Xm EIKT. Means m times lambda plus ik minus lambda J equal to 0. This is the. So here is for the Bengale-Dirac normal form for autonomous system, Bengale-Dirac normal form for periodic system. Yes. For any system, for example, for the system 6, the system always can be transformed to this form. This is a near identity transformation. This is a linear part. This is a higher order term in Y. This is the invertible. This change is the invertible. Transform it to this system. Given a system, autonomous or periodic system, always there exists change. This change can be analytic or formally. Change to this system in Bengale-Dirac normal form. But this transformation is convergent or not. This is the important problem. In the history, on this problem, there are many very important, very nice results to prove this transformation. This transformation we call it the normalization. This transformation we call it the normalization. This normalization convergent or not. This is in the title of my talk is analytic normalization, means that we want to prove this transformation is convergent. Yes, since our case is partially integrable, we separate the eigenvalue in two parts. Lambda prime, lambda 2 prime. This is from lambda 1 to lambda L. This is from lambda L plus 1 to lambda N. So correspondingly, the system can be written this way. Since this lambda prime, lambda 2 prime, the eigenvalues are different. So different, so the linear part can be separated. So the system 6, we write in this form. Later we dilute by X star this vector field associated to this system. Now we define what is the Bengale normal form or invariant manifold. Yes. Here, if x2 prime equal to 0, this equal to 0, then x2 prime equal to 0 is the invariant for this system. If restricted to x2 prime equals 0, this system only depends on x prime. So this system is in Bengale-Dirac normal form. We say that this system is normal form on invariant manifold. So x2 prime equals 0, this equals 0 means that x2 prime equals 0 is invariant for this system. Then restrict to x2 prime equals 0, this system only depends on x1, x prime. If this system is in Bengale-Dirac normal form, then we say that this system is in Bengale-Dirac normal form on invariant manifold. Okay. Yes. Do you remember this mu is the eigenvalue of the Bengale map? This lambda is the eigenvalue of the matrix A. The relation between these eigenvalues, mu j equal to E I K lambda j, has this relation. Yes, we don't want to say this one. Yeah. I also don't want to say this. Yeah, here is yes. Yes, this is our second result. Say that if the eigenvalues lambda prime, this lambda j belong to L plus 1 to n, so this lambda j belong to lambda 2 prime. Means that lambda prime, these two eigenvalues, yes, here. We separate eigenvalue lambda in two parts, lambda prime, lambda 2 prime. So the assumption means that these two parts do not resonate each other. Yeah, this condition. This lambda j belong to lambda 2 prime. So this condition means that these two eigenvalues, two parts, do not resonate each other. If the system has L minus 1 functionally independent analytic first integral, and I lost mu j not all there. Some can be real. Here is mu j not all there. I lost them all. Yeah. Then the system 10 is this one. Yeah, this one. This system 10. Then system 10 is analytically equivalent to the normal form on invariant manifold. This is one of the main results. Yeah. This is some remark. We said this theorem extends our previous result. Yeah. Yes, I have the remark. I say the system, the number of functionally independent analytic first integral no less than d mu. Do you remember? D mu is the maximum number of functionally independent elements in the rational lattice. But if the first integral is not analytic or not formal, this result is not correct. Since in 2024, I with our two co-authors published one paper, say that for planar system has a saddle, the eigenvalue do not resonate, but the system we construct a C infinity first integral. I say if the system has a saddle, if the two eigenvalues are not resonant, then the system do not have analytic first integral. Also do not have formal first integral. But they can have C infinity first integral. So, yeah. Yes. Just we say about the existence of normalization. Now we want to extend the the result from planar to higher dimension. For the planar analytic system, if system the origin is the center, then the origin has a neighborhood full of periodic orbit. This region is a two-dimensional. Yes? Since the periodic orbit full of a neighborhood of the origin, so this region is a two-dimensional. We extend this result to higher dimensional. If the analytic system too has a periodic orbit, and also this, yes, and the system has the maximum number d functionally independent analytic first integral, we have another assumption. This functionally analytic first integral, the gradients are full rank everywhere. Then there exists a d plus one dimensional subregion. This subregion full of periodic orbit. So this is the extension from two-dimensional to higher dimensional. If the system has d functionally analytic first integral, and also the gradients are full of rank everywhere, then the system can have d plus one dimensional subregion. This subregion full of periodic orbit. Yeah, in fact, this result at the very beginning, we write that this previous to this theorem with this theorem and another one in one paper. But we submitted to the Journal of Differential Equation, but the referee said, no, this is not good to put these together. Only the first two is good for publish. So we separate these two parts for another paper. Only the first two theorem published in the Journal of Differential Equation. So these do not publish now. As I mentioned, this theorem, we say this system is an analytic system, has analytic first integral. But if replaced this analytic by only ck smoothness, then in the complete integral C cases, the theorem is also correct. But for this case, partially integrable, the system may be not correct. Since just I mentioned, maybe the system has other first integral, C infinity first integral. Yes, this is the last one I want to characterize, give a new criterion on characterize the isochronal center. This planar system, the origin is a monodromy. The monodromy is rotated. As we know, if the system has an analytic first integral, then origin is the center. But until now, do not have any result. Use the first integral to characterize isochronal center. Do not have any result. Only have this result. Just if this system has an isochronal center at the origin, if and only if the system is analytically linearizable at the origin. This is a characterization. To characterize this system the origin is a isochronal center or not, we only has one gradient to characterize this system. This system is analytically linearizable at the origin. Now we provide a new gradient to characterize. The system has the origin is the isochronal center. Use the first integral. Now a result is the following. The planar analytic system has the origin is an isochronal center with period 2 pi. These all, since this origin is an isochronal center, so all the orbit has the same periodic orbit, has the same period. So we always can change the time. Change time such that the period becomes 2 pi. So the system has an origin as an isochronal center with period 2 pi if and only if the system has an analytic first integral in this form. in this form. This f is x plus higher order term, the g is y plus higher term. So here we give a new criterion to characterize isochrolus center with this first integral. So this is the main result. I want to give the talk. If I have time, I want to give a sketch proof of this result here. This is the main result here. Yes. Do you remember? I mentioned for our theorem 1 and theorem 2 stayed in periodic system. Our theorem 1, theorem 2 stayed in the periodic system. Six periodic system is this one. When we started the ordinary differential, we say, given a system, if we have an invertible change of coordinates to a new system, then if the original system has some number of functionally independent first integral, then the transformed system also has the same number of functionally independent first integral. This is easy to prove. Here I state this system 2 is an autonomous system. System 13. Yeah. This in fact system 6 I write in this form. This 13 and 6 are same. If system 2 H is the first integral of system 2, then after this change, we change system 2 to system 13. Use the same change, then this periodic system has this first integral. Conversely, if this system 13 has a first integral, then we use the invertible change, then go back. This P is the first integral of original autonomous system 2. This is easy to prove. Now, we want to know, since this is a periodic system, the first integral usually is periodic in T. But if we go back, use the invertible change, go back to the original system 2, this first integral is independent T or not. This is important. In fact, we can prove that if the system is no, sorry. Yes. Yes, it's here. Yes. If system is partially analytically integrable, then we can prove that this periodic system has this first integral. This first integral after the change of under the invertible change go back to the system 2. This first integral must be independent of T. So this first integral is also autonomous. This is good information. To have this property, then we studied the theorems 1.1 and theorem 1.2 stated in the periodic system. Then we can go back to the autonomous system. Yes. Now we want to give a sketch proof. We go back proof from the last one to the first one. The last one is the system has an origin as an isochrolus center if and only if the system has an analytic first integral in this special form. This proof is easy. First, we prove sufficiency. If the system has a first integral in this form, then we prove that the origin is isochrolus. We only use the definition. If this is the first integral, then use the definition of the first integral. We can get this equation. This equation can be written in this form. You see, this is a linear system. We say the origin is an isochrolus center if and only if the system is linearly integrable. So this is the proof. And conversely, necessarily, if the system can be linearly writable, then this system has a first integral in this form. Then we go back, we have this first integral. This proof is easy to prove. Now we go back to the theorem 1.3. We recall the theorem 1.3 said, if the partially integrable analytic system has d functionally independent analytic first integral whose gradients are full rank everywhere, and the system has no singularity in the region, then the system has d plus 1 dimensional subregion. This subregion full of periodic orbit. Well, now we want to prove this one. But for two-dimensional, this is obviously. So we separate in 3 cases. N equal to 2 system has a first integral. This is a known result. Now we consider d larger than 2 and n larger than 2 is high dimensional. And the system is completely integrable. Has n minus 1 function independent first integral. Then we use reduction to prove our result. First we use for L equal to 2, so here is n minus 2. The level set, we have n minus 2 level set intersect, then is a two-dimensional. Two-dimensional system has two-dimensional first integral, two-dimensional region full of periodic orbit. Then we use L equal to 3. We add another first integral, along each periodic orbit. We use this one we can get another dimensional. So we get a 3-dimensional region full of periodic orbit. Then we use the reduction to prove that this system has n-dimensional subregion full of periodic orbit. In the partially integrable cases, we use the center manifold. Since we have d-dimensional, a d-functionally independent first integral, so we use the center manifold theorem. Then we have d-dimensional, you have d plus 1 dimensional center manifold. In the normal direction is the normal direction. Yes. In normal direction, the system has no periodic orbit. The only possible is on the d plus 1 dimensional manifold. So on this d plus 1 dimensional center manifold, then we can use the case 2 result to get the result. Here is I only mentioned this one. In the proof, I write several pages to write this one. Yeah. I only mentioned how to prove. If you are interested, I can send you the preprint to you. Yeah. So now we prove the theorem 1.1 and theorem 1.2. Here we use the Bengala-Dirac normal form and also prove their convergence. Yeah, this is an important property. Property 4.1. If the system 6, just we say any system always can be transformed to this distinguished normal form, but the normal form, the normalization is convergent or not, we don't know. We always can write the system in the Bengala-Dirac normal form. Yes. So this XS is the semi-simple part. So any matrix A, we can write in semi-simple part and the near-opponent part. So this XS denotes the semi-simple part of the linear vector field, the linear part of the system 6. Then this semi-simple part has d functionally independent positive first integral. It's easy to prove. Use the assumption. Then The periodic system 6 has D functionally independent analytic or formal first integer if and only if this system has D admits every pseudo monomial first of this XS. This is a reduction to study the functionally independent first integral can be reduced to this semi-simple part. But this system must be in normal form, generally not correct. If the system in distinguished normal, yes, I forget to say what is distinguished. Distinguished means the transformation. We transform the system 2 to system 6. If the transformation do not have the resonant term, then the transformation called the distinguished, and the system is called the distinguished normal form. That are the proof we need to use this proposition. This proposition can be found, this is the extension from the autonomous system to periodic system. Yes, the proposition is the extension of this paper has a similar proposition, but for the autonomous system. Our case is the system has a periodic orbit near the periodic orbit. So yes, we also need another proposition. Just we say we separate the eigenvalue in two parts. These two eigenvalues do not resonate each other. Correspondingly, we separate A in these two parts. Yes, we need this A prime is a diagonal. We have, yes. I don't want to say more about this proposition, only mention this one. Yes. Now we want to prove theorem 1. Theorem 1 says there exists a series psi such that after this action, it becomes only composed of the pseudo monomial. If the system is partially integrable, then the alternate coefficients are equal to 0. The third one is on the system has this special form of the first integral. Now we want to prove this theorem 1.1. Yes, the first statement is easy to prove. Since we use this L dilute this partial differential operator is the partial t, partial x. Okay, now the vector field here, this is partial t. This vector field acts on this psi exactly this linear operator L. You see partial t. This is the vector field acts on this one. This is the linear part. So this partial differential operator acts on this psi. This left side exactly this one. This is the same. After expansion, we have this one, this one, this one. Then for here, since this operator L on the non-resonant part is invertible, so we can cancel the non-resonant part, only remain the resonant part. Each part are same. The operator on the non-resonant part, the operator is invertible. Then we cancel the non-resonant part, only remain the resonant part. So finally, we can get here only remain the resonant part. Each non-resonant can be cancelled. Use the invertible of the operator. Now we prove for this one, we use the normal form. We use this original system after the near identity change to this system. This system in normal form. So just the propositions for this normal form system, we have this result. We go back to here. We say if the system in normal form, then the system 6 has D functionally independent analytic or formal first if and only if this system has the pseudo monomial first integral of this semi-simple system. We use this one, yeah. Yes. So from here to here, we only the calculation here. By contradiction, if to prove theorem B, if this is not equal to 0, then we get here some calculation. Then we get a contradiction. I don't want to say more. Now we go back to the statement C. Yes. For C, we always can transform the original system 6 to Bangladesh normal form. Then use the Bangladesh normal form. Our original system has D functionally independent first integral. Then the normal form system also has D functionally independent first integral. Then we use this YS has this monomial, pseudo monomial first integral. Then we use the near identity change, go back to the original system, we can get this one. Here we only use the normal form. We can prove the result. Yeah, so yes, for the last one is theorem 1.2. To prove this theorem, we need the next result. This result can be found in, this is a book by Wei Li from Beijing University, but this theorem also can be found given by I think it's Brewer. The book has this theorem. If the eigenvalues do not resonate each other, then always there exists a near identity formal change. This change only depends on y prime, do not depend on y2 prime. The nonlinear part only depends on y prime, such that the original system can be transformed to the normal form on invariant manifold. Now, next time we only need to prove this transformation is convergent or not. The system, under this condition, the system can be transformed to the normal form on invariant manifold. This is a long result. So now we want to prove this transformation is convergent. Yes, now we restate our theorem. Under this condition, the system has this number of function independent first integral between mu j not all 0. Then the system analytically equivalent to the normal form on invariant manifold. This is here is normal form. In fact, this is the y2 prime equal to 0. This is equal to 0. So here, on y2 prime equal to 0, this system is the normal form system. This is near identity. This is linear part. This is a higher term. This is a pure. This is only a function, one-dimensional function. This is a linear part. So now we prove this convergent. Convergent, we separate in 3 steps. First, use the long result. The system can be transformed to the normal form on invariant manifold. Then we prove that if this non-resonant condition is satisfied, then the norm always has a bounded, lower bounded. So here do not have the small divisor condition. Then we prove that this change are convergent. This change is convergent but this is more involved this part. We expand all these functions in Taylor Fourier series. Then we estimate this h in the transformation. Use g is here. This is the g. This is phi. And h is in the transformation. I think h. Yeah. H is here. H is the transformation. We want to prove this transformation, this h prime, h2 prime are convergent. We do not separate, we put together to prove they're convergent. Now to prove the convergent. This F1, F2 prime is known. This is the inner transformation. This is in the normal form. We expand all these functions in Taylor Fourier series. Then we use the Jornadas series to estimate. We put all these things in together. This is the in transformation. This is the in normal form. We want to prove all these things are convergent, put together. Then after some, if here we said, given the concrete expression of this part is more involved. This part. After this, use this expression, we can estimate all these series. Then we use the implicit function theorem to prove that. Since use this inequality, we can construct an analytic function. Use the implicit function theorem, we can prove that since if an analytic function can be used the implicit function theorem, then the solution is analytic. We use this estimate, we construct an analytic function, then we use the implicit function theorem to prove that the system has an analytic solution. Then this analytic solution is a majority series of this function. Then all these series are convergent. It's proved. So my talk is here. Thanks.
So thank you, Professor. Is there any questions? Comments? No questions or comments? Yeah, please.
Thank you, Professor Zhang.
Zhang.
I guess the technical part on the convergence of this transformation is very cumbersome. But I want to ask if the techniques are the same that are used in proving the Kolmogorov-Arnold-Moser, when you have to use a Newton method to get the convergence, or not? Or why?
Part of yes. Part of yes.
Okay.
Yeah, part of yes.
But in this condition, does the existence of an invariant manifold helps to simplify these techniques?
Of course, yes.
Okay.
Since the system is partially integrable or analytically integrable, then we do not have the small divisor condition.
Okay.
Usually, the system, if do not have the early restriction, usually the eigenvalues is most possible has a small divisor condition. Since the system is integrable or partially integrable, then we do not have the small divisor condition.
Okay.
Yeah, this simplifies the proof. Yeah, you're correct. Thanks.
Thank you.
Yeah.
Yep. Do you have more questions or comments? Okay. Yeah.
Thank you for your talk.
Thanks.
I am not sure if I am understanding. I am physicist.
Yeah.
And when you have a system which is isochronous, I would expect that this property reduce the number of the possibilities. So you must have some integral, some first integral, additional first integral, and maybe is what you were proving. So I would expect that the isochrony of the system implies some first integral, as the Kepler problem, for instance, which has the Runge-Laplace vector. Is it true?
But now we do not have application now. I don't know. So maybe in the future we try to apply. Maybe I know. Now we do not have the application, so now I don't know yet. Yes.
Okay.
This is interesting. Yeah.
Okay. Thank
So
you.
we do some mathematics. Always want to combine with the physics. Yeah. Really. Yeah. Thanks. Yeah. Thanks.
Do you have more questions or comments? Okay, well, if not, we thank again Professor Xiang.
Okay. Thanks.
So, yeah, thank you very much for being here. On Wednesday, we will have another talk at the same time. So we hope to see you again on Wednesday. So, thank you. On Wednesday. Yeah.
Okay. Thanks.